In this video, we want to start the process of learning how to calculate the area under a curve. So for example, if I had the curve in blue, bounded by these two vertical lines in black, I'm going to eventually want to know how to calculate the area under the curve down to the x-axis. Now, we know how to calculate the area of regular shapes, rectangles, trapezoids, circles. But when it comes to an irregular shape, we don't know how to calculate at the moment the area under that. So, as with most things, when we don't know how to do something, we build on what we do know how to do and try to adapt that to our new situation. So what I have here is I have a curve in blue, and I'm going to use 4 rectangles to approximate the area under the curve. So I'm going to calculate the area of these 4 rectangles, and that will be my estimate for the area under the curve. Now granted, my estimate's going to be off because my rectangles are going above the curve, so my estimate will be more than the actual area under the curve. However, if I were to increase the number of rectangles eventually to 8 or 16 and so on, you'll notice that the amount of space above the curve with all of these rectangles is less and less, and so the estimate provided by the rectangles will become more and more accurate the more that we have as we increase the number towards infinity. Okay? In fact, until they're so small that you can't even see the rectangles individually. Okay? Now, you might wonder, going back to my 4 rectangles, why I chose to use this distance as the height. Okay? This distance right here is the y value on the right side of the interval. Okay? I could just as well have used the left side to determine the height of the rectangle. So let me just change this over to left. And for example, if I take a given interval, this is my 3rd rectangle, the height that I'm using is the y value for the value of x on the left side of the interval. Okay? And if I now find the area of all of these rectangles, I'm going to get an estimate that's less than the actual area under the curve. And in fact, I could have taken any point in the interval. I could have taken the middle. So for a given subinterval, to determine the height, I'm using the middle x value, the y value that goes with that, to determine the area of this. The length times the width will be the area of this rectangle. And this estimate using midpoint in this particular example should provide an answer that's probably closer than in any of the other 2 estimates for the area under the curve. But again, as we increase the number of rectangles endlessly, taking the area of more and more rectangles, we'll get closer and closer to the actual area under the curve. Okay, let's approximate the area under the curve using this specific example. We have the function y equals x squared, and we want to approximate the area under the curve between x equals 1 and x equals 3. Using 4 rectangles, remember the more the better, but for now we're just going to do 4. And we're going to use the left endpoint to determine the height of each rectangle. So I'm going to break this interval into 4 sections. And since we're going between 3 and 1, which is 2 units, and dividing it into 4, I know that my width for each rectangle will be 1/2. Okay? So this distance here I'm labeling as delta x. Now the height, we want to use the distance on the left where this hits the curve. And this is going to be the y value for the given x value, which I'm going to label as f of x sub k, k being the interval, interval 1, interval 2, interval 3. So we want our y value on the left to be the height of the rectangle. So there's rectangle 1, rectangle 2. The y value on the left is the height of the rectangle. And you'll notice that when I draw these, my rectangles are under the curve, so my estimate will be lower than the actual area under the curve. Alright, and just for the record, these x values here, since they're a half a unit apart, that would be 1.5, 2, that would be 2.5, and 3. Alright, so now we're ready to find the sum of the 4 rectangles. And so for rectangle 1, it's going to be the height times the width. So the y value on the left is f of 1 times a half. For rectangle 2, it's the y value for 1.5 times a half, rectangle 2. For rectangle 3, it's f of 2 times a half. And for the fourth rectangle, it's f of 2.5 times a half. Okay. Now, if I wanted to write that in sigma notation, just so you see how that connects to what we already know about sigma notation, I could write the sigma of f of x sub k times delta x. This is the width, this is the height, and we're doing it for the 4 intervals, from interval 1 up to interval 4. Okay, this is equivalent to this. You could also write your expression above as 1/2. You can think of taking the constant out front. So it's 1/2 of f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. And if you work all of that out, you're going to get 6.75, which is our estimate, which will be lower than the actual area under the blue curve because the rectangles are all below. By the way, approximating the area under the curve using rectangles is called a Reimann sum, after the person who came up with this particular method. Okay? And as I mentioned before, we could use the left side or the right side or the middle of the interval to, as the y value to determine the height. In this example, I've just used the left. Another method that's used to approximate the area under the curve is the trapezoid method. And that is similar to the rectangles, except that when we divide the interval into, let's do 4 parts again, our trapezoids are going to look like so. I'm going to connect each endpoint . So what I'm actually drawing is a curve like so. Okay, and this is a trapezoid because these two sides are parallel. Now you'll remember that the area of a trapezoid is 1/2 the height times the sum of the two parallel sides. So this would be the A and B. The height here would be the same as delta x when we did rectangles. Now you can see that the trapezoid method in general should probably give a more precise approximation to the area under the curve than rectangles would. Alright, let's continue with this and do the sum of the 4 trapezoids. So trapezoid number 1 will be 1/2 times the height of a half times A and B, which would be f of 1 plus f of 1.5. Trapezoid 2 would be, again, a half times a delta x of a half times f of 1.5 plus f of 2. Trapezoid 3 a half times a half times f of 2 plus f of 2.5, and trapezoid 4 a half times a half times f of 2.5 plus f of 3. Now by the way, when you simplify this expression, all of these 4 terms have a half times a half. This was the delta x, remember, and multiply by all of these. So we're going to have f of 1, we're going to have 2 f of 1.5s, we're going to have 2 f of 2s, we're going to have 2 f of 2.5s, and we're going to have 1 f of 3. And if you work all of that through, the sum of the 4 trapezoids would be 8.75. So in general, the sum of 4 trapezoids is 1/2 the sum of the 4 trapezoids of height times a plus b. F of x sub k plus f of x sub k plus 1.